Have you ever stood outside on a clear, dark night and gazed up at the stars, feeling that profound sense of awe wash over you? Out there, in the seemingly infinite blackness, lies a cosmos teeming with mysteries we are only just beginning to understand. For centuries, humanity has looked to the skies with a mix of curiosity and wonder, searching for answers to our deepest questions. Yet, the universe has a way of speaking to us in whispers rather than shouts, subtle, enigmatic signals that drift across the vastness of space, waiting to be decoded. These are not just random bursts of energy or cosmic static. They are deliberate, puzzling messages from the far reaches of existence, and they hold secrets that could reshape everything we think we know. Imagine, if you will, a silent conversation taking place across billions of light years. A signal travels for eons through the cold vacuum, carrying with it the signature of events so colossal and strange that our minds can barely grasp them. From repeating fast radio bursts that defy explanation to strange, rhythmic pulses that hint at celestial phenomena beyond our current understanding, the cosmos is sending us clues. It's as if we're piecing together an interstellar puzzle, one where every new discovery raises more questions than it answers. What are these signals trying to tell us? Are they natural cosmic symphonies, or could they be something more, something intentional? In this journey together, we're going to explore 25 of the most enigmatic signals ever detected, each one a story written in the language of the universe itself. We'll unravel the science behind these cosmic whispers, from the famous WOW signal that stunned astronomers to strange emissions that seem to echo from the edges of reality. This isn't just about facts and data. It's about the thrill of the unknown, the shared human drive to uncover truths hidden in the stars. So settle in, open your mind to the possibilities, and get ready to venture into a world where every signal could be the key to unlocking the next great mystery of our existence. Our journey into the cosmos's greatest mysteries begins with perhaps the most famous, and certainly the most evocatively named, signal ever recorded, the WOW signal. It was a seemingly ordinary evening on August 15, 1977, at the Ohio State University's Big Ear radio telescope. This massive instrument was silently scanning the heavens, part of the ongoing search for extraterrestrial intelligence, or SETI, program, patiently listening for anything out of the ordinary. And then, for exactly 72 seconds, it heard something that was anything but ordinary. A narrowband radio signal, blazingly intense, erupted from the speakers. It came from the direction of the constellation Sagittarius and was concentrated on one specific frequency, 1420 MHz. This frequency is not random, it's a cosmic landmark. 1420 MHz is the emission frequency of hydrogen, the most abundant element in the universe. The thinking was that any intelligent civilization attempting to announce its presence might use this universal, natural radio station as a clear channel, a logical place to send a signal that would be recognized as artificial. And this signal was a perfect example. It was loud, it was focused, and it was completely unlike the usual background static of the cosmos. When volunteer researcher Jerry Amon reviewed the computer printout days later, he was so astonished by the sheer power of the signal that he circled the alphanumeric sequence representing its intensity, which read 6 = QU, and scribbled a single, powerful word of amazement in the margin: WOW. The name and the story stuck, but the mystery only deepened. The Big Ear telescope was fixed to the Earth's rotation, so any signal from space would only be in its view for 72 seconds, which is exactly how long the WOW signal lasted. It peaked and then faded away exactly as expected. The search for a repeat began almost immediately. Astronomers pointed telescopes at that same patch of sky again and again for decades. They listened for hundreds of hours, but the signal never returned. It was a one-time event, a single, brilliant shout into the cosmic silence that was never followed by another word. This singular nature is what makes natural explanations so difficult to accept. Could it have been a reflection from a piece of human-made space debris? The frequency was protected. Terrestrial transmissions were forbidden on that band precisely to avoid such confusion. A military satellite, no known satellites matched the signal's profile, and it's hard to imagine one that would transmit such a powerful, pure signal just once and then never again. A comet. This was a popular theory proposed decades later, suggesting hydrogen clouds around comets could be the source. But the specific comets proposed weren't even in that part of the sky on that date. Each proposed natural cause seems to fall short, failing to explain the signal's unique combination of strength, frequency, and its frustrating refusal to ever be heard again. So we are left with a profound puzzle, a cosmic whisper that has echoed for decades. Was it a one-time astronomical event we simply don't yet understand? Or was it something else, a fleeting, intentional beacon from a distant civilization, a message that swept over our planet and was gone before we even knew how to properly reply? The WOW signal endures not because we have an answer, but because it perfectly represents the tantalizing promise and deep frustration of the search. It is the signal that got away, a ghost in the machine that continues to inspire us to listen just a little more closely to the stars. If the WOW signal was a single, mysterious shout in the dark, then fast radio bursts are the universe's relentless, high-energy chatter. These are not gentle whispers, they are colossal explosions of radio wave energy that travel across unimaginable distances, packing more power in a single millisecond than our sun emits in 80 years. Their story begins not with a circled notation on a printout, but with a forensic search through archived data. In 2007, a young astronomer named Duncan Lorimer was sifting through old observations from the Parkes radio telescope in Australia, searching for new pulsars. What he found, buried in data from 2001, was something entirely unprecedented. A 5-millisecond spike of radio energy so powerful and so isolated that it defied all known categories of cosmic events. It had traveled for billions of years to reach us, and in that fleeting moment, it announced the existence of a phenomenon we had never even imagined. The sheer scale of energy involved in an FRB is what makes them so difficult to comprehend. Picture the most powerful nuclear bomb ever detonated. Now imagine detonating 500 million of those bombs all at once and focusing all of that energy into a beam of radio waves lasting less time than the blink of an eye. That is the raw, violent power of a typical fast radio burst. For years, every single one of these events was a one-off, a solitary flash in the cosmic pan that left astronomers scratching their heads. Theories about their origins ranged from the catastrophic, like the final death cry of a star being shredded by a black hole, to the speculative, including the possibility of immense interstellar engines powering alien light sails. Everything changed in 2016 with the identification of a source known as FRB 121102. This was the game changer, the repeater. Unlike all the others that flashed once and vanished, this one, located in a dwarf galaxy 3 billion light-years away, did something extraordinary. It burst again. And again, it wasn't a single catastrophic event. It was a source that was persistently, though unpredictably, active. This crucial discovery ruled out any theory that required the source to be destroyed in the process, like a stellar collision or an explosion. The repeater told us that whatever is creating these bursts is somehow surviving them, pointing toward an object that can unleash these titanic energies repeatedly, like a cosmic geyser. This led the search for a culprit to some of the most extreme and magnetic objects in the universe, magnetars. A magnetar is a type of neutron star, the ultra-dense corpse of a massive star, but with a magnetic field so incredibly powerful it defies belief. To put it in perspective, a magnetar's magnetic field is a quadrillion times stronger than Earth's. If a magnetar were located halfway between Earth and the Moon, it would effortlessly wipe the data from every credit card on the planet. The thinking is that these stars can experience starquakes, immense ruptures on their crystalline surfaces, that snap their magnetic fields, releasing a staggering amount of energy in a fraction of a second, potentially creating an FRB. Observations have since strengthened this link with our own galactic magnetar, SGR 1935 plus 215, emitting FRB-like bursts, providing a nearby template for these distant monsters. Yet, perhaps their most profound gift to science isn't the mystery of their origin, but the information they carry within their signal. As an FRB travels across the universe, it doesn't move through empty space. It plows through the dilute gas and plasma that exists between galaxies. This material slows down the radio waves, and crucially, it slows down lower frequencies more than higher ones. By measuring this smear, this delay between the arrival of the high and low frequencies, a property called the dispersion measure, astronomers can effectively count the number of electrons the signal encountered on its journey. Each FRB becomes a cosmic dipstick, measuring the amount of invisible, diffuse matter it passed through. By using thousands of these bursts, we are beginning to create a three-dimensional map of the missing ordinary matter in the cosmos, the very bones of the universe's large-scale structure that have eluded us for decades. But this monumental discovery almost didn't happen. The initial reaction within the astronomy community was one of profound skepticism. Could such a brief, powerful signal truly be cosmic? The more logical explanation seemed to be a terrestrial glitch, an instrumental error, or perhaps a military signal from a satellite that had been misidentified. The signal's unique characteristics, particularly its high dispersion measure, strongly argued for an extragalactic origin, but without a second example, the Lorimer Burst remained an intriguing anomaly, a celestial ghost that many were hesitant to believe in. It was the ultimate cosmic detective story, a single piece of evidence so extraordinary that it demanded an extraordinary burden of proof. The breakthrough lay in that very dispersion measure, the telltale smear of frequencies. By calculating how much the lower frequencies were delayed compared to the higher ones, astronomers could estimate the vast distance the signal had traveled. The math was staggering. The Lorimer Burst had journeyed from a source an estimated 3 billion light-years away. To grasp the energy required for a signal to remain detectable after such an epic voyage, consider this comparison. In that single, fleeting millisecond, it released more energy than our Sun emits over a period of 30,000 years. It was a deflagration of almost incomprehensible power, a brief storm of radio waves that had crossed a third of the observable universe to etch its mark onto a data tape in Australia. This one event, pulled from the archives, single-handedly carved out an entirely new field of astrophysics. It was the catalyst. It provided the template, the unique fingerprint that researchers could now actively search for in real-time data streams from telescopes around the world. The Lorimer Burst was the proof of concept that such phenomena not only existed but were potentially common once we knew how to look for them. It transformed the search from a retrospective analysis of old data into a vibrant global hunt, leading to the discovery of hundreds more FRBs and the classification of both one-off bursts and mysterious repeating sources. Duncan Lorimer's archival find was the key that unlocked a hidden door in the cosmos, revealing a universe crackling with transient, energetic events we are only now beginning to decipher. While the wow signal and the explosive power of fast radio bursts captivate our imagination, there's another signal that presents a different kind of puzzle, one not of immense power or singular brilliance, but of persistent, maddening ambiguity. This is the story of SHB-02+14a, a signal that didn't announce itself with a bang, but with a faint, tantalizing whisper that has divided astronomers for decades. Discovered in 2003 by the SETI at Home project, this signal embodies the immense challenge of separating a genuine cosmic hello from the ever-growing cacophony of human noise. SETI at home was a revolutionary concept. Instead of relying on a single giant telescope, it harnessed the spare processing power of millions of personal computers around the world. Volunteers would download a screensaver that quietly analyzed small chunks of radio telescope data from the massive Arecibo Observatory, looking for the telltale signs of an artificial signal, a narrow bandwidth and a steady, drifting frequency. The idea was that a signal from a planet orbiting a distant star would not be perfectly fixed. The Doppler effect caused by the planet's motion around its star and the star's motion through space would cause the frequency to shift slightly over time, creating what astronomers call a drift rate. SHGB 02 plus 14 had exactly that. It was detected 3 times at a frequency very close to the universal water hole of 1420 MHz, and it exhibited a drift rate that was consistent with a transmitter located on a planet orbiting a star at a plausible speed. On the surface, it seemed to check all the boxes for a potential candidate, but this is where the mystery deepens and the controversy begins. The signal was impossibly weak, so faint that it was right at the very edge of what the equipment could even detect. Its point of origin in the constellation Pisces didn't correspond to any known stars or planetary systems within 1,000 light-years. It was, as one scientist memorably put it, coming from a place of absolute nowhere, a seemingly empty patch of space. Furthermore, the signal's behavior was strange. It was only ever detected for less than a minute at a time, and it appeared to be circularly polarized. This type of polarization is rare in nature but common in human-made technologies like satellite communications. This single characteristic immediately raised a giant red flag, pointing toward a terrestrial or orbital source. The most likely explanation, and the one most critics support, is that SHGB 02 plus 14 was nothing more than an artifact of human technology, a case of celestial eavesdropping. The signal's frequency is perilously close to those used by television satellites and other orbital transmitters. The thinking is that the Arecibo telescope, incredibly sensitive as it was, might have picked up a faint reflected signal. A transmission from a satellite could have bounced off a piece of space debris or even a patch of the Earth's atmosphere, creating a distorted, drifting signal that fooled the algorithms into thinking it was from deep space. This kind of interference is the bane of SETI researchers, a constant reminder that our own technological bubble makes it incredibly difficult to hear the universe clearly. Yet, despite the overwhelming evidence for a terrestrial origin, a small sliver of doubt remains, and this is what keeps SHGB 02 plus 14 on the list of intriguing enigmas. The fact that it was detected on 3 separate occasions, months apart, argues against it being random noise or a one-time glitch. A transient reflection from space junk would be unlikely to repeat in exactly the same way. Its specific drift rate, while not impossible to generate artificially, still fits a profile that SETI scientists would expect from an extraterrestrial transmitter. In the end, the signal is a perfect example of the SETI paradox. It was just unusual enough to be interesting, but not strong or persistent enough to be conclusive. It lives in a frustrating gray area, a ghost that we can neither confirm nor completely dismiss. A reminder that the greatest discovery in human history might be hiding in the faintest of whispers, waiting for us to listen just a little more carefully. While the signals we've explored so far are fleeting bursts or faint whispers, some cosmic mysteries announce themselves with a slow, deliberate, and utterly bewildering fade. This brings us to one of the most talked about stellar anomalies of the 21st century, KIC 8462852, better known as Tabby's star or the alien megastructure star. Unlike a sudden radio blast, this puzzle wasn't discovered in a moment of shock, but painstakingly unearthed from mountains of data by a team of citizen scientists. The star, located about 1,400 light-years away in the constellation Cygnus, was being monitored by NASA's Kepler Space Telescope, whose primary mission was to find exoplanets by detecting the telltale, repeating dips in starlight that occur when a planet passes in front of its host star. Most stars in the Kepler database showed these predictable, symmetrical dips. Tabby's star did not. It was and remains in a class of its own. The data revealed a light curve that defied all conventional explanation. Instead of the clean, periodic dips of a planet, the star exhibited enormous, irregular dimming events. At one point, the star's light dropped by a staggering 22%. To put that in perspective, a Jupiter-sized planet would only block about 1% of a star's light. This was something vastly larger and completely asymmetrical, as if a huge, ragged swarm of objects was passing in front of it. The dips had no consistent periodicity. They would appear, last for days or weeks, and then vanish, only to return months later in a completely different pattern. One particularly deep dimming event lasted for almost a week, while others were sharp and dramatic. This wasn't the signature of a simple, spherical planet. It was the signature of chaos. Naturally, the most exciting and provocative theory emerged almost immediately. Could this be evidence of an alien megastructure? The concept, popularized by physicist Freeman Dyson, imagines an advanced civilization capable of harnessing the entire energy output of its star by constructing a vast swarm of orbiting collectors, a Dyson sphere. Such a structure wouldn't be a solid shell, but a messy, uneven network of panels and habitats that would block starlight in an irregular, non-repeating way, perfectly matching the bizarre light curve of Tabby's star. The idea captured the public's imagination like few other astronomical discoveries, transforming a distant sun into a beacon of potential cosmic companionship and turning its discoverer, Tabitha Boyajian, into a household name. Of course, scientists rightly pursued every possible natural explanation first. The leading theory proposed a massive, fragmented swarm of comets. The idea was that a family of exocomets, perhaps disturbed by the gravity of a nearby star, could be on a long, eccentric orbit around Tabby's star. As they approached the star, they would break apart, creating a huge cloud of dust and debris that could account for the deep, irregular dimming. Other hypotheses included a recent planetary collision that had filled the system with swirling dust, or a vast, warped ring system around a giant planet. Yet each of these natural models struggled to fully explain the observations. For instance, follow-up observations searching for the excess infrared heat that such vast amounts of dust should produce came up largely empty, leaving the comet swarm theory on shaky ground. The mystery only deepened with a look into the star's past. Astronomers combing through historical photographic plates discovered something even more astonishing. Over the past century, Tabby's star appears to have undergone a significant long-term dimming. Analysis showed its overall brightness had faded by as much as 14% between the 1890s and the 1980s. This was completely unprecedented for a star of its type. While stars can vary in brightness, this kind of steady, century-long fade is not normal behavior. It added another layer of profound mystery, suggesting that whatever was causing the short-term dips might also be responsible for a much larger, gradual obscuration. Intensive follow-up campaigns, including a massively successful Kickstarter-funded project that allowed astronomers to continuously monitor the star, have provided more data but no definitive answers. We've witnessed more dimming events in real time, confirming the phenomenon is ongoing. Detailed spectroscopy during these dips has shown that the light is being blocked by ordinary dust grains, as different colors of light are blocked to different extents. This seems to rule out a solid, opaque megastructure which would block all light equally. So while the dust discovery appears to put a damper on the most exotic theory, it actually brings us right back to a fundamental question. What is producing this incredible amount of dust in such bizarre, unpredictable patterns? The natural processes we know about don't easily create such colossal, dynamic dust clouds around a mature star. So where does that leave us today? the alien megastructure hypothesis, while not completely ruled out, has retreated in favor of more natural, if still highly unusual, explanations. The current best guess points toward a complex and dynamic circumstellar environment, perhaps still reeling from a catastrophic event like a moon-sized body breaking apart, creating a shifting, evolving cloud of fine debris that continues to orbit the star. Yet, the century-long dimming remains a haunting, unsolved part of the puzzle that no theory comfortably addresses. Tabby's star endures not as a confirmed sign of aliens, but as something perhaps equally valuable, a profound reminder that there are still fundamental processes at work in the universe that we have not yet witnessed or even imagined. It is a cosmic puzzle box, challenging our assumptions and proving that sometimes the most compelling signals aren't pulses or bursts, but a star that simply, mysteriously winks. Just as we were grappling with the long-term dimming of a distant star, a new signal appeared from tantalizingly close to home, reigniting the debate about our cosmic neighbors. In the closing months of 2020, the Breakthrough Listen project, the most comprehensive scientific search for extraterrestrial intelligence ever undertaken, detected something extraordinary. Their Parkes radio telescope in Australia, affectionately known as the Dish, was observing our closest stellar neighbor, the Proxima Centauri system, a mere 4.2 light-years away. Proxima Centauri is a red dwarf star, and we know it hosts at least 2 planets, one of which, Proxima Centauri b, orbits within the star's habitable zone where liquid water could theoretically exist. It was during these planned observations that the system seemed to talk back. The team's algorithms flagged a narrowband radio signal at 982 MHz, a frequency typically quiet and free from human satellite interference. They designated it Breakthrough Listen Candidate 1, or BLC-1. The initial excitement was palpable, and for good reason. BLC-1 checked several key boxes for a potential technosignature. It was a narrowband signal, meaning it was concentrated on a single, specific frequency, a hallmark of an engineered transmission rather than a natural astrophysical event. It exhibited a clear drift rate. Its frequency changed slightly over time in a way that was consistent with the movement of a transmitter located on a planet orbiting the Proxima Centauri star. Most compellingly, the signal appeared only when the telescope was pointed directly at Proxima Centauri and vanished when it was pointed away, a crucial test that seemed to rule out local interference. For a brief, thrilling moment, it seemed like the discovery everyone had been waiting for might have come from literally the next star over. However, in science, extraordinary claims require extraordinary evidence, and the initial excitement was quickly tempered by a wave of rigorous skepticism. The Breakthrough Listen team themselves led the charge to debunk their own candidate, adhering to the highest scientific standards. The first major red flag was that the signal was never detected again despite extensive follow-up observations. A deliberate beacon from another civilization would presumably be persistent or repeating, not a single, fleeting event. The second, and ultimately definitive, problem emerged from deeper analysis. While the signal itself was narrowband, the researchers discovered it was actually composed of multiple tones or harmonics that were spaced apart at regular intervals. This specific harmonic structure is a fingerprint of human technology, often generated by oscillators in electronic devices. The most likely explanation, though still not perfectly pinpointed, points not to the stars but to our own planet. The leading theory is that BLC-1 was a form of intermodulation distortion. This occurs when 2 or more strong radio signals from human sources, perhaps a nearby cell phone tower, a satellite, or even a faulty electronic device on the observatory grounds, accidentally mix together inside the sensitive receiver of the telescope itself. This mixing creates a new, phantom signal at a frequency that is the mathematical difference between the 2 original signals. This phantom can appear to drift and behave in ways that mimic a genuine extraterrestrial transmission, especially if the original interfering signals themselves are intermittent. It was a case of the universe playing a cruel trick with our own technology, a sophisticated form of radio frequency pollution that even the most careful observing protocols can sometimes fail to catch. Despite the ultimate classification of BLC-1 as human interference, its legacy is far from negative. The entire episode served as an invaluable drill, a real-world test of the entire process of candidate verification. It demonstrated that our detection systems are sensitive enough to find needle-in-a-haystack signals, and that the scientific community is capable of subjecting such finds to intense, critical scrutiny without letting hype overshadow facts. Furthermore, the event reinforced the importance of continuing to search around red dwarf stars like Proxima Centauri. These small, cool, and incredibly common stars were once dismissed as unlikely hosts for life due to their tendency to unleash violent flares of radiation. However, the discovery of rocky planets in their habitable zones has made them prime targets. Any civilization that evolved on such a world would likely be far hardier than our own, and the proximity of these systems makes them ideal for detailed study. The story of BLC-1 is not a story of failure, but a masterclass in scientific caution and a reminder that the most alluring signals often require us to look first and most critically at ourselves. Sometimes the most profound cosmic revelations begin with a simple, meticulous act of checking the data. In 1967, a young Cambridge doctoral student named Jocelyn Bell Burnell was poring over miles of chart paper recorded by a radio telescope she had helped build. The instrument was designed to study the twinkling of distant quasars, but Bell noticed something else entirely, a peculiar, repetitive scratching on the readout that didn't look like any known celestial object or terrestrial interference. It was a steady, precise pulse, arriving every 1.337 seconds with a regularity that was almost unnerving. In a universe dominated by chaotic and variable signals, this was different. It was too perfect, too mechanical. As more of these pulses were detected, the only logical conclusion seemed to be the most exciting one imaginable. This had to be a beacon. The team half-jokingly labeled the source LGM-1 for Little Green Men. The idea wasn't as far-fetched as it might sound today. If an advanced civilization wanted to announce its existence across the vastness of space, a precisely timed radio pulse would be an efficient and unmistakable calling card. The thought that they might have stumbled upon the first evidence of other intelligent life was both thrilling and terrifying. The small research group was plunged into a state of heightened secrecy and intense debate. They quietly discussed the societal implications of such a monumental discovery, while simultaneously searching for any possible flaw in their equipment or analysis that could explain the signal away. The tension was palpable. They were sitting on what could be the biggest news in human history, but they had to be absolutely certain. That certainty came not from finding a message in the pulses, but from finding more of them. The key breakthrough arrived when Bell discovered a second, similar signal emanating from a completely different part of the sky. The odds of two separate civilizations independently deciding to beam the same type of signal at Earth were vanishingly small. The signal wasn't artificial, it was natural. The source was soon identified as a rapidly spinning neutron star, the ultra-dense, collapsed core of a massive star that had gone supernova. As this cosmic cinder rotates, it sweeps a beam of intense radiation across space, much like a lighthouse beam sweeping across the ocean. Every time that beam passes over Earth, we detect a pulse. They had discovered the first pulsar, and LGM-1 was renamed CP1919. A designation that belied its revolutionary nature. The impact of this discovery cannot be overstated. It fundamentally reshaped our understanding of stellar evolution, providing the first direct evidence for the existence of neutron stars, objects that had been theorized but never observed. It revealed a new class of celestial objects with incredible physical properties, where a teaspoon of material would weigh billions of tons. For the field of SETI, the pulsar discovery was a bittersweet lesson that proved invaluable. It created a rigorous protocol for extreme skepticism. Before any signal can be seriously considered a candidate for extraterrestrial intelligence, astronomers must first rule out every possible natural astrophysical phenomenon, no matter how bizarre or seemingly artificial it appears. The pulsar became the gold standard for a false alarm, a reminder that the universe is capable of producing its own perfect-looking beacons. Jocelyn Bell Burnell's role in this story also highlighted a profound and sadly ongoing challenge within science. While her doctoral advisor, Anthony Hewish, shared the 1974 Nobel Prize in Physics for the discovery, Bell herself was controversially excluded from the recognition, a decision still debated as a classic example of the systemic overlooking of junior researchers and women in science. Yet her perseverance and keen eye unlocked a window into the most extreme physical environments in the universe, teaching us a humbling and crucial lesson: that nature often possesses an ingenuity that can, for a breathtaking moment, mirror our wildest dreams of who else might be out there. For a while, the hunt for fast radio bursts was haunted by a mischievous doppelganger, a signal that perfectly mimicked the key characteristic of these cosmic bursts but had a far more mundane and frankly hilarious origin. These imposters were dubbed Puritans, a name chosen from mythological lore for a winged stag that casts a human shadow. It was a fittingly mysterious title for signals that looked for all the world like they came from deep space but were, in reality, casting a very earthly shadow. Their story is a brilliant and at times embarrassing cautionary tale about the challenges of cleaning data and the unexpected ways human activity can interfere with our quest to understand the universe. The Puritans first appeared in data from the Parkes Radio Telescope in Australia, the same instrument that had discovered the first FRB. They shared a crucial feature with their cosmic counterparts, a dispersion measure. Like a true FRB, lower frequencies of a Puritan arrived at the telescope slightly later than higher frequencies, creating that telltale smear across the spectrum that indicates a signal has traveled through a vast amount of interstellar plasma. This was the gold standard for confirming an extragalactic origin. The Puritans passed this test, convincingly masquerading as visitors from distant galaxies. Yet something was off. While FRBs are pinpoint events in the sky, Puritans were detected across multiple beams of the telescope's receiver simultaneously. This meant the source wasn't a distant point of light but something much closer, flooding the entire dish with radio noise. The mystery of the Puritans persisted for years, a nagging puzzle that cast a faint shadow of doubt over the entire FRB field. Were some of these bursts actually local phenomena? The breakthrough didn't come from a complex astronomical model, but from simple, boots-on-the-ground detective work. An observatory staff member finally noticed a crucial correlation. The Puritan signals were only ever detected during the workday, and specifically around lunchtime. The culprit, it turned out, was the staff microwave oven. If an observant researcher was particularly hungry and opened the oven door before the timer had fully finished and clicked off, the magnetron inside would emit a brief, powerful burst of radiation at 2400 MHz. This burst was just the right frequency to be detected by the telescope's receiver. But how did a microwave burst create a dispersion measure, the key signature of a deep space journey? The answer was brilliantly simple and had to do with the telescope's own design. The radio waves from the microwave didn't travel through interstellar plasma. They traveled a few dozen feet through the air and then bounced off the telescope's metal dish. The signal's path to the receiver at the dish's focus was slightly different for different frequencies. This minute difference in path length, created by the reflector's geometry, imposed a delay that perfectly mimicked the dispersion effect of a signal that had journeyed millions of light years. The universe wasn't playing a trick. The telescope's own structure was converting a mundane human impatience into a convincing cosmic cipher. The resolution of the Puritan mystery was a triumph of scientific diligence and humility. It forced radio astronomers to develop even more rigorous data vetting protocols. The key differentiator became that multi-beam detection. A true FRB will only appear in a single, specific beam of the telescope, corresponding to its precise point of origin in the sky. Any signal that appears across multiple beams is immediately flagged as local interference. This event underscores a fundamental truth in the search for rare cosmic phenomena. The greatest challenge isn't always collecting the data, but meticulously cleaning it of the countless fingerprints we ourselves leave behind. It's a never-ending process of distinguishing the faint whisper of the universe from the constant, low hum of our own civilization. While many cosmic explosions announce themselves with a brief, violent flash, some events unfold with a strange and beautiful slowness, leaving behind a luminous fingerprint that puzzles astronomers for years. This brings us to an event so unique it earned a festive nickname, the Christmas Burst, officially known as GRB 10-1225A. Detected by NASA's Swift satellite on December 25, 2010, this gamma-ray burst didn't behave like any other. Instead of the typical short, intense flash followed by a rapidly fading afterglow, this burst began with a peculiar 50-second-long emission of gamma rays and then did something extraordinary. It kept shining. Its afterglow lingered for an astonishingly long time, fading so slowly that it remained visible in X-ray and optical light for more than a week, a drawn-out cosmic encore that defied all standard classifications. The initial challenge for astronomers was simply figuring out what kind of event they were witnessing. Gamma-ray bursts are traditionally sorted into two neat categories. Long bursts lasting more than 2 seconds are associated with the core collapse supernova deaths of massive stars. Short bursts under 2 seconds are linked to the violent mergers of ultra-dense objects like neutron stars. The Christmas burst, with its 50-second duration, should have fit neatly into the long category, yet it lacked the definitive smoking gun accompanying supernova. Telescopes searched intently for the telltale rise in light from an exploding star in the burst's host galaxy, but they found nothing. It was a long burst without its defining feature, a cosmic outlier that played by its own set of rules. This absence of a supernova forced astrophysicists to consider far more exotic and violent scenarios. One of the most compelling and imaginative theories proposed a stellar catastrophe of almost biblical proportions, the impact of a massive celestial body, like a comet or a small planet, onto a neutron star. Imagine a neutron star, a city-sized object with a density so immense that a sugar cube-sized amount of it would weigh more than 1 billion tons, wandering through its own planetary system. If a large, rocky or icy body in that system were pulled into a collision course by the star's immense gravity, the resulting impact would be unimaginably powerful. As the object plowed into the neutron star's atmosphere, it would be torn apart, creating a titanic explosion and generating a jet of gamma rays fired into space. The infalling debris would continue to feed the explosion for an extended period, perfectly explaining the burst's long duration and the persistent afterglow that followed. However, a different team of researchers later proposed an alternative and equally fascinating explanation. Their analysis pointed toward a source much, much farther away, suggesting the Christmas burst was not a local collision but a distant, unusual supernova after all. Their model described a rare event known as a fallback supernova. In a typical supernova, the explosion blasts the star's outer layers into space, leaving behind a dense core. But in a fallback supernova, the explosion is somehow weaker or fails to fully ignite. Some of the ejected material doesn't achieve escape velocity and instead falls back onto the newly formed neutron star or black hole at the center. This raining down of stellar debris would create a prolonged emission of energy as the material spirals in and is consumed, accounting for the burst's long, smooth tail of X-rays without the bright optical signature of a normal supernova. The debate between these two models, a local stellar impact versus a distant, failed supernova, highlights the incredible challenge of interpreting these brief flashes of light from across the universe. The Christmas burst's true nature likely lies in one of these camps, but its legacy is far greater than solving a single mystery. It forced astronomers to expand their playbook and acknowledge that the universe's violent events don't always conform to our tidy categories. It became a key data point in the study of atypical gamma-ray bursts, proving that there is a spectrum of stellar deaths and cosmic collisions, each with its own unique signature. This single, strangely beautiful burst serves as a permanent reminder that for every rule we devise to explain the cosmos, there is always an exception waiting to be discovered, a celestial gift that keeps on giving long after the festive lights have dimmed. The discovery of that first Lorimer burst was just the opening chapter in a story that has since exploded into one of the most dynamic and fast-moving fields in all of modern astronomy. For years after that initial find, every new detection was a major event, a hard-won prize pulled from the data. Each one was a one-off, a brilliant and solitary flash that left astronomers with more questions than answers. The central mystery was agonizing. What could possibly create such unimaginable energy in a millisecond and then be completely destroyed or simply vanish? The hunt was on, not just for more bursts, but for a pattern, a clue that could crack the case wide open. That crucial breakthrough arrived in 2016, transforming the entire field overnight. It came from the same patch of sky that had already given us so many puzzles, the constellation Auriga. There, a source designated FRB 121102 did the unthinkable. It repeated. Unlike all the others that flashed once and were never heard from again, this one burst again and then again. It wasn't a single, catastrophic event. It was a persistent source, a cosmic geyser that erupted unpredictably, sometimes remaining quiet for weeks before unleashing a furious storm of multiple bursts in a single day. This single discovery shattered the prevailing theory that all FRBs were born from events that destroyed their source, like a neutron star collision or a black hole devouring a star. Suddenly, we knew that whatever was creating these signals was robust enough to survive the outburst, pointing the finger squarely at objects that could unleash these titanic energies repeatedly, like the immensely powerful magnetos. This fundamental split between one-off bursts and repeating sources created the first major classification system for these phenomena and hinted at the possibility of multiple different origins. The one-offs, incredibly powerful and never heard from again, could still be the signature of a singular, catastrophic event. The repeaters, often less energetic but persistently active, pointed toward a different type of engine, one that could fire over and over. This distinction forced theorists back to the drawing board, and it was the newly commissioned Canadian Hydrogen Intensity Mapping Experiment, or CHIME, that would provide the data to fuel their work. Unlike traditional dish telescopes that must be pointed at specific targets, CHIME is a revolutionary stationary array. It has no moving parts. Instead, it uses sophisticated digital signal processing to stare at a huge swath of the sky all at once, 24 hours a day, 7 days a week. It is, effectively, a celestial surveillance camera, and it was perfectly designed to catch these fleeting, unpredictable events. Almost immediately after coming online in 2018, CHIME began to revolutionize our understanding. It didn't just find a few FRBs, it began to discover them by the dozens, then by the hundreds. Its relentless, wide-eyed gaze revealed that these events were not rare cosmic oddities at all. Current estimates suggest that somewhere in the observable universe, 1,000 of these bursts are going off every single day. CHIME's enormous haul of data allowed for the identification of many more repeating sources, confirming that repetition was a genuine property of a significant subset of these events and not just a fluke. More importantly, by pinpointing the locations of these bursts to their host galaxies, CHIME and other telescopes began to paint a stunning cosmological picture. FRBs were not coming from any one type of galaxy. They were being detected in huge elliptical galaxies, in spiral galaxies like our own Milky Way, and in tiny, chaotic dwarf galaxies that were still vigorously forming stars. This universal distribution proved that the source of these bursts was not tied to a specific, rare galactic environment, but was a fundamental process that could occur almost anywhere. This incredible volume of data has elevated FRBs from mere curiosities to powerful tools for cosmic exploration. Because each burst signal is smeared by the tenuous material it passes through, every FRB acts as a natural probe of the otherwise invisible matter that exists in the vast voids between galaxies. By analyzing the dispersion of thousands of these signals from different distances and directions, astronomers are beginning to construct a three-dimensional map of this missing baryonic matter, the ordinary atoms that theory predicts should exist but had largely eluded detection. We are now using these mysterious flashes not just as objects to be understood themselves, but as lighthouse beacons to illuminate the dark, lonely stretches of the cosmic web, turning a profound mystery into one of our most promising new instruments for mapping the universe itself. Despite the initial excitement, the true scientific legacy of the WOW signal lies not in its detection, but in the decades of determined effort to find it again. The original Big Ear telescope was decommissioned in the late 1990s, but its mystery only grew, inspiring a series of increasingly sophisticated follow-up campaigns. In the late 1990s and again in the 2000s, astronomers pointed the massive Very Large Array, or VLA, in New Mexico toward the coordinates of the signal. The VLA is a vastly more sensitive instrument, a network of 27 individual radio dishes that work together as a single, colossal telescope. If there was any persistent or repeating signal coming from that point in Sagittarius, the VLA would have heard it. The result, however, was a profound and definitive silence. Not a whisper, not an echo. The signal that was once louder than the background noise of the entire cosmos had vanished without a trace. This frustrating lack of recurrence is the core of the mystery and has fueled a constant cycle of new theories and counter-theories. One of the more creative natural explanations proposed involved a phenomenon known as gravitational microlensing. The idea was that a massive but invisible object like a rogue planet or a small black hole could have passed directly between a distant, steady source of radio waves and Earth. The object's gravity would act as a lens, briefly bending and focusing the radio waves, amplifying a faint, otherwise undetectable signal into a powerful burst for just a few moments before it faded away as the lensing object moved on. This would elegantly explain both the signal's intensity and its one-time nature. However, the chances of such a perfect alignment are astronomically low, and no evidence for the lensing object or the background source has ever been found. A more recent and highly publicized explanation came from researcher Antonio Paris in 2016. He proposed that the signal could have been caused by a cloud of hydrogen surrounding a passing comet. Two specific comets, 266P/Christensen and 335P/Gibbs, were suggested to have been in the right part of the sky on that August night. As comets approach the Sun, they release vast clouds of gas, primarily hydrogen, which could theoretically emit radio waves at that magic frequency of 1420 MHz. This theory gained a lot of traction in the media, but it was met with immediate and strong skepticism from the astronomy community. Critics pointed out that the comets in question were far too faint and their hydrogen clouds far too diffuse to produce a signal even remotely as powerful as the one detected. Furthermore, the Big Ear telescope used two separate feed horns that viewed the sky slightly apart from each other. A signal from a moving comet should have appeared in both horns minutes apart as the sky drifted by, but the WOW signal was only ever detected in one. Beyond the scientific debate, the WOW signal's most enduring impact has been cultural. It became the quintessential symbol for the entire SETI endeavor, a single data point that perfectly captures the thrilling possibility of contact and the agonizing ambiguity that comes with it. It transformed the search from a purely theoretical exercise into a tangible human drama. That single word scribbled in a margin, "Wow," did more to capture the public's imagination than any technical paper ever could. It was a moment of raw human wonder preserved in the scientific record, a reminder that at the heart of all this complex technology and data analysis are people who are genuinely awestruck by the universe. The signal story is taught in classrooms, featured in documentaries, and has inspired countless works of science fiction, cementing its place as the most famous non-detection in the history of astronomy. It stands as a permanent beacon of curiosity, a reminder that sometimes the most important discoveries are not the answers we find, but the profound and enduring questions we are left to ponder. While the WOW signal remains a decades-old cold case, a much more recent detection sent a similar, albeit much shorter, jolt of excitement through the astronomical community. In the spring of 2016, just as the field was grappling with the implications of the first repeating fast radio bursts, another signal emerged that seemed to tick all the right boxes. This one was detected not by a conventional dish, but by the Ratan 600 radio telescope in Zelenchekskaya, Russia. This instrument is a truly unique piece of engineering, a circular array of radio-reflecting panels that form a giant stationary ring nearly 600 meters in diameter. On May 15, 2015, it recorded a strong narrowband signal at a frequency of 11 gigahertz, apparently emanating from the vicinity of a Sun-like star known as HD 164595, located 94 light-years away in the constellation Hercules. The star itself was an intriguing target. It's slightly larger and brighter than our own Sun, and we knew it hosts at least one Neptune-sized planet, HD 164595b, in a very tight, hot orbit. While that planet itself is unlikely to be habitable, its existence suggested the possibility of other, as yet undiscovered worlds in the system that could be more Earth-like. The signal itself was reported to be quite strong, and the narrowband nature made it a prime candidate for a technosignature. The news, however, didn't become public until a year later, in late August 2016, when an Italian astronomer named Claudio Maccone circulated a memo to a small group of SETI researchers, suggesting the signal warranted further investigation. When the story broke publicly, it ignited a media firestorm. Headlines around the world buzzed with the possibility of a signal from an advanced civilization just 94 light-years away, a stone's throw in galactic terms. The specific strength of the signal, as initially interpreted, fueled intense speculation. Some calculated that if the transmission were being broadcast in all directions, it would require a truly staggering amount of energy, far beyond what our entire civilization could produce. However, if it were a tightly focused beam deliberately aimed at our solar system, the power requirements became much more plausible for a civilization only slightly more advanced than our own. For a brief, electrifying moment, it felt like history might be repeating itself, but this time with a signal that was current and potentially verifiable. The scientific response, however, was characterized not by panic, but by a swift and coordinated global effort to verify the claim, a testament to how much the field had matured since the days of the WOW signal. Unlike in 1977, astronomers now had a worldwide network of telescopes and a well-established protocol for rapid response. The SETI Institute immediately tasked the Allen Telescope Array in California to stare at HD 164595. The Green Bank Telescope in West Virginia joined the hunt, as did the Buckwheat Optical SETI Observatory in Panama, which searched for coordinated laser pulses. This was a full-court press, leveraging the best technology across the planet to either confirm or deny the signal's existence. The results were definitive, and they came back almost immediately. Nothing, not a whisper. Every follow-up observation of the star turned up empty. There was no repeat signal, no trace of any unusual activity. The initial excitement quickly gave way to a more sober assessment. The most likely explanation, as is so often the case, pointed squarely back to Earth. The Rattan 600 telescope has a very wide field of view, and the signal's characteristics were highly suspicious. The frequency of 11 GHz is heavily used for terrestrial and satellite communications, including by the Russian military. The most plausible scenario was that the telescope had picked up a stray signal from a secretive Russian satellite or some other piece of human technology that happened to pass through its beam. It was a classic case of terrestrial interference fooling a sensitive instrument, a modern-day Puritan. The HD 164595 episode, while ultimately a false alarm, provided an incredibly valuable lesson for the SETI community. It highlighted both the promise and the peril of the modern era. On one hand, it demonstrated our newfound capacity for rapid response. The ability to mobilize a global network of telescopes within hours of a candidate signal being announced is a powerful capability that will be crucial for authenticating any future discovery. On the other hand, it underscored the ever-growing challenge of radio frequency interference in an increasingly crowded orbital environment. Our own technological bubble is making the cosmic search harder, not easier. Furthermore, the incident sparked an important debate about the protocols for announcing potential signals. Many argued that the results should have been thoroughly vetted by the broader scientific community before being leaked to the public, to avoid the kind of media frenzy that can damage the credibility of the search. The story of the HD 164595 signal is not a story of failure, but a successful drill that tested our systems and reinforced the critical need for patience, skepticism, and rigorous verification in the enduring quest to answer humanity's oldest question. Just as we were beginning to categorize fast radio bursts into repeaters and one-offs, the universe delivered a curveball that defied all expectations, a burst with a heartbeat. This is the story of FRB 180916, a source that didn't just repeat randomly, but did so with a precise, predictable rhythm that sent theorists into a frenzy. Discovered by the CHIME telescope in Canada, this repeater, located in a spiral galaxy 500 million light-years away, exhibited a pattern so regular it seemed almost engineered. For 4 days it would erupt with multiple bursts, a period of intense cosmic activity. Then, for the next 12 days, it would fall completely silent. This cycle of activity and quiet repeated exactly every 16.35 days, over and over again like clockwork. This was unprecedented. For the first time, we weren't just detecting chaos, we were detecting cosmic order, a rhythm written into the fabric of deep space. The immediate and most thrilling question was, what could possibly cause such a precise periodicity? Natural astronomical systems often have rhythms. Planets orbit stars, stars spin on their axes, moons orbit planets. But a 16-day cycle for an object capable of generating millisecond bursts of incredible power. The theories quickly branched into 2 distinct camps. The first and most popular natural explanation involves an orbiting system. Imagine a highly magnetized neutron star, a magnetar, in a long, eccentric orbit around another massive object, perhaps a companion star or even a black hole. For most of its orbit, the magnetar is too far away for anything unusual to happen. But when it swings in close to its periastron, the point of its closest approach, the immense tidal forces from the companion object could trigger starquakes on the magnetar's surface or disrupt its magnetosphere, unleashing the powerful burst. The 4 days of activity would correspond to this close encounter, while the 12 days of silence would be the rest of its long, slow orbit. This model provides an elegant, clock-like mechanism to explain the on and off nature of the burst. However, the sheer regularity of the cycle also inevitably fueled speculation about an artificial origin. Could this be a beacon, the idea of a purposeful, periodic signal is a cornerstone of SETI theory. A civilization might use a powerful, repeating transmission on a predictable schedule as a way to efficiently announce its presence across the galaxy. The 16-day period is strange. It's a long time for a technological signal, but not impossible. Perhaps it's aligned with some fundamental aspect of their world, their calendar, or their orbital mechanics. The temptation to see design in such a perfect pattern is a powerful one, a direct echo of the LGM-1 pulsar discovery decades earlier. Yet, as with all such signals, the burden of proof is immense. The scientific principle of seeking natural explanations first firmly places the orbiting model as the leading candidate, but the mere existence of such a perfect pattern ensures the artificial hypothesis remains a tantalizing, if remote, possibility in the back of our minds. The true power of FRB 180916, however, lies not in speculation but in a monumental achievement of observational astronomy, its precise localization. Using a network of radio telescopes across Europe known as the European Very Long Baseline Interferometry Network, or EVN, astronomers were able to pinpoint the source of these rhythmic bursts with stunning accuracy. They didn't just identify the host galaxy, they zoomed in on a specific region within it. The FRB was originating from a spiral galaxy similar to our own Milky Way, but crucially, it wasn't located in the chaotic, star-forming regions of the galactic outskirts where most young magnetars are born. Instead, it was positioned in a more sedate, suburban region of the galaxy, an area where star formation is relatively quiet. This location immediately ruled out models that required a highly active, violent environment, forcing a reconsideration of what kind of object could create such power in a seemingly calm neighborhood. This precise address provided another crucial clue. The region was coincident with a persistent, compact radio source. This faint, steady radio glow could be the smoking gun, the engine itself. It might be a luminous nebula powered by the magnetar's fierce winds, or perhaps the remnant of the supernova that originally created the neutron star. This persistent source acts like a cosmic signpost, pointing directly at the system responsible for the brilliant, repeating flashes. The discovery of FRB 180916 and its rhythmic behavior did more than just add another strange object to the catalogue. It fundamentally changed the game. It proved that at least some FRBs are not only repeatable but can be governed by predictable clockwork mechanics rooted in orbital motion. It gave theorists a specific, testable model to work with, moving the field from pure speculation into the realm of detailed astrophysical modeling. This burst, with its steady 16-day heartbeat, reminds us that even in the most energetic and chaotic corners of the universe, there is often an underlying order waiting to be discovered. While we often think of signals as bursts of energy or radio waves, sometimes the universe sends us a messenger, a physical object that drifts into our solar system carrying secrets from the void between stars. This brings us to a discovery that redefined the very meaning of a cosmic signal. In October 2017, the Pan-STARRS telescope in Hawaii detected a faint point of light moving at breathtaking speed. Its trajectory was immediately and stunningly clear. It was not from here. It was the first interstellar object ever observed passing through our solar system, and it was given a name that reflected its role as a scout from afar, Oumuamua, Hawaiian for a messenger from the distant past arriving first. Its origins were just the beginning of the mystery. As astronomers around the world trained their telescopes on this visitor, two bizarre characteristics emerged. First was its shape. By measuring how its brightness changed dramatically as it tumbled through space, researchers deduced that Oumuamua was not a typical roundish asteroid or comet. It was highly elongated, perhaps 10 times longer than it was wide, like a cosmic cigar or a pancake tumbling end over end. This was a form rarely seen in our own solar system and suggested it had endured a unique and violent formation process in its home system billions of years ago. The second and far more perplexing anomaly was its motion. As Oumuamua traveled away from the Sun, it did not follow a purely gravitational path. Something was giving it an extra push, a slight but undeniable non-gravitational acceleration. For a normal comet, this is easily explained. Heat from the Sun vaporizes ice on its surface, creating jets of gas and dust that act like tiny thrusters. But Oumuamua showed no visible signs of this activity. No surrounding coma of gas, no tail of dust. It was moving like a comet but looked utterly inert, like a bare rock. This contradiction between its behavior and its appearance was the central puzzle that launched 1,000 theories. The scientific community scrambled for natural explanations. One of the most elegant proposed that Oumuamua was in fact a comet after all, but one made of something more exotic than water ice. The leading candidate was molecular hydrogen ice. A hydrogen iceberg, if you will, such an object theorized to form in the coldest, densest cores of giant molecular clouds could sublimate, turn directly from a solid to a gas under the Sun's heat. Because hydrogen gas is invisible to telescopes, this would explain the acceleration without a visible tail. However, many physicists were skeptical, questioning whether a fragile hydrogen iceberg could have survived a multi-million-year journey through interstellar space without being evaporated by starlight or torn apart by cosmic rays. The absence of a conventional explanation inevitably opened the door to more speculative ideas, most famously championed by Harvard astronomer Avi Loeb. He suggested that the object's unusual acceleration and peculiar shape were consistent with a light sail, a thin, artificial object designed to be pushed by the radiation pressure from starlight. In this scenario, Oumuamua wasn't a natural asteroid but a piece of advanced technology, perhaps a defunct probe or a discarded piece of equipment from an alien civilization drifting through the galaxy. While Loeb himself was careful to state this was a possibility to be considered, the idea captured the global imagination, transforming the object from a scientific curiosity into a cultural icon, and a fierce debate about how far we should go in considering artificial origins for unexplained phenomena. Ultimately, Oumuamua's greatest legacy may not be which theory proves correct, but the profound way it has shifted our perspective. It demonstrated that interstellar objects are not rare theoretical constructs. They are a tangible reality, likely passing through our inner solar system with surprising frequency. It forced us to realize that a cosmic signal doesn't have to be a beam of energy. It can be a physical artifact, a silent, tumbling relic from another star. This visitor challenged our classifications and our assumptions, proving that the universe is far more inventive than we are. It left as quickly as it arrived, vanishing into the darkness beyond Neptune, but it left behind a permanent change in astronomy, awakening us to the fact that the next great messenger from the cosmos might not be a flash in the data, but a rock tumbling through our own backyard. The search for life beyond our solar system often focuses on finding a planet that looks like home, a world of just the right size, orbiting in the temperate Goldilocks zone of its star, where temperatures might allow for liquid water. In 2010, the announcement of such a world around the nearby star Gliese 581 sent waves of excitement through the scientific community and the public alike. Gliese 581g, as it was named, wasn't just another exoplanet. Preliminary data suggested it was a rocky world, about 3 to 4 times the mass of Earth, orbiting squarely within its star's habitable zone. It was, on paper, the most promising candidate for a potentially habitable planet ever discovered. And then came the even more tantalizing rumor that astronomers had detected a mysterious, possibly artificial signal coming from its direction. The star itself, Gliese 581, is a red dwarf located a mere 20 light-years from Earth in the constellation Libra. Red dwarfs are the most common stars in our galaxy, but they are notoriously tempestuous, often prone to violent flares that could strip the atmospheres from any nearby planets. This particular star was already known to host a family of planets, but Gliese 581g, the fourth planet proposed in the system, seemed special. The team behind the discovery, led by astronomer Stephen Vogt, used years of precise radial velocity measurements tracking the star's subtle wobbles caused by the gravitational tug of orbiting planets to infer its existence. The statistical significance of their find was strong enough for Vogt to famously declare that he was 100% certain there was life on this world. It was a bold statement that immediately set the stage for both celebration and intense scrutiny. Amidst this fervor, a rumor began to circulate within the SETI community, later reported in the media that a signal had been detected. The story, which seemed to blur the lines between fact and fantasy, originated from a source within the Australian SETI community. It was claimed that the Parkes radio telescope had picked up a suspicious signal, a single, unexplained spike that appeared to originate from the vicinity of the Gliese 581 system. The signal was reportedly narrowband, a key characteristic of an engineered transmission, and it had been detected not once but twice. This combination, a potentially habitable world and a curious signal from its location, was irresistibly compelling, creating a perfect storm of public intrigue and scientific skepticism. However, the scientific process is designed to temper excitement with rigorous verification, and almost immediately, other teams began to challenge the very existence of the planet. A separate group working with a larger, more comprehensive dataset from the HARP spectrograph in Chile reanalyzed the stellar wobbles. Their results were starkly different. They found no statistically significant evidence for Gliese 581g at all. The signal Vogt's team had interpreted as a planet, they argued, was actually just noise in the data, the result of the star's own magnetic activity and starspots masquerading as a gravitational pull. The astronomical community was suddenly divided, with one team insisting the planet was there and another insisting it was not. Without a consensus on the planet's existence, the idea of a signal from it became exponentially more speculative. The alleged signal itself quickly unraveled under investigation. The SETI Institute, along with the researchers involved with the Parkes telescope, conducted a thorough analysis. Their conclusion was definitive. The signal was not extraterrestrial. It was terrestrial interference, a radio frequency contaminant. The culprit was believed to be technology right here on Earth, likely a military communication satellite or other human-made transmitter whose signal had reflected off space debris or the Earth's atmosphere and into the telescope's receiver. It was a sophisticated form of electronic echo, a ghost created by our own technology that momentarily tricked the detection systems. The two detections were not a repeat signal from deep space, but two separate instances of the same type of local interference occurring months apart. The entire Gliese 581g episode serves as a powerful, multifaceted cautionary tale for the modern age of exoplanet hunting. Firstly, it highlights the immense difficulty of detecting tiny Earth-sized planets using the radial velocity method, especially around active, noisy red dwarf stars. The signals astronomers are looking for are incredibly faint, buried in data that can be corrupted by the star's own behavior. It underscores why independent confirmation from multiple research groups is an absolute necessity before any revolutionary discovery can be accepted. Secondly, the signal aspect of the story demonstrates the ever-growing challenge of radio frequency interference. As our planet becomes enveloped in an increasingly dense shell of satellite transmissions and wireless communications, the task of finding a genuine cosmic signal becomes like trying to hear a whisper at a rock concert. It forces SETI researchers to develop ever more sophisticated filters and validation protocols. Ultimately, the story of Gliese 581g is not about a discovery that was made, but about the painstaking process of distinguishing hope from reality. It's a story that unfolds not in the thrill of detection, but in the quiet, meticulous work of analysis and peer review. The planet itself remains officially unconfirmed, a ghost in the data that some still argue for and others dismiss. But its legacy is cemented. It taught us that the path to finding another Earth is fraught with false positives and sobering setbacks, reminding us that in the search for cosmic company, our greatest tools are not just powerful telescopes but patience, skepticism, and an unwavering commitment to the evidence. While the initial data from Kepler provided the stunning revelation of Tabby's star's bizarre behavior, the story was far from over. The real scientific journey began with a monumental effort to keep a constant, watchful eye on this unpredictable star, an endeavor that quickly outgrew the resources of any single observatory. This is where the global community, both professional and amateur, stepped in. The star's discoverer, Tabitha Boyajian, launched a Kickstarter campaign that became a stunning testament to public fascination with cosmic mysteries. The campaign, titled "The Most Mysterious Star in the Universe," soared past its goal, raising over $100,000 from more than 1,700 backers in just 30 days. This funding was crucial. It purchased dedicated time on a global network of ground-based telescopes, ensuring that Tabby's star could be monitored continuously, night after night, across different longitudes. This meant that whenever the star decided to dim, someone somewhere would be watching. This crowdsourced vigilance transformed the study of the star from analyzing old data to conducting a real-time stakeout, turning citizen scientists into essential partners in the hunt for answers. This persistent monitoring quickly paid off. In May 2017, the star delivered, putting on its most spectacular show since the original Kepler observations. Over a period of several days, it underwent a series of significant dimming events, with its light dropping by up to 3% at a time. Because the global network was poised and ready, astronomers were able to capture this activity in incredible detail across the entire electromagnetic spectrum, from radio waves to ultraviolet light. This was the breakthrough moment. By analyzing the starlight that filtered through whatever was blocking it, researchers could perform a kind of cosmic spectroscopy, identifying the material's fingerprint. The critical clue came from the color of the dimming. The observations showed that blue light was being blocked more than red light. This is the definitive signature of dust. Small, microscopic dust grains scatter blue light more effectively, which is why our sky is blue and sunsets are red. A solid, opaque object like a megastructure would block all colors of light equally, creating a neutral dimming across the spectrum. The color-dependent dimming observed was a near-conclusive blow to the alien megastructure hypothesis, firmly pointing toward a natural explanation involving clouds of fine particulate matter. So if the culprit is dust, the question simply shifts. What is generating such immense, dynamic, and irregular clouds of dust around a mature star? The leading theory now suggests a complex and ongoing catastrophic event in the star's planetary system. Imagine a scenario where a large, comet-like body or even a moon-sized planetesimal was gravitationally disrupted, perhaps by a close encounter with a giant planet or a collision with another body. This event would have shattered the object into a vast swarm of fragments and an enormous cloud of fine debris. This cloud, spread out along a highly elliptical orbit, would continue to circle the star. As different parts of the swarm, with varying densities and clumps, pass in front of the star from our viewpoint, they would cause the irregular and deep dimming events we observe. The long-term, century-long fading could be explained by a broader, more dispersed disk of dust created from this same event, slowly drifting inward or spreading out to create a persistent haze. This model elegantly explains the erratic behavior without requiring any fundamentally new physics, relying instead on known orbital mechanics and the aftermath of violent collisions. However, even this compelling dust theory faces its own challenges. The sheer amount of dust required to cause the deepest dimming events is staggering, and such a massive cloud should radiate a significant amount of absorbed stellar energy as heat, which should be detectable as excess infrared radiation. Yet, searches for this infrared glow have come up largely empty. This missing infrared energy remains a key puzzle. Some researchers propose that the dust particles could be unusually large and porous, like fluffy snowflakes, which are very effective at blocking light but less efficient at absorbing and re-radiating heat. Others suggest the dust cloud is located very far from the star, where it would be much colder and thus emit its faint heat at far infrared wavelengths that are more difficult for our current telescopes to detect. While the dust model is the prevailing theory, this missing infrared signature ensures the mystery retains a layer of depth, reminding us that our understanding of circumstellar debris, even around our own sun, is still evolving. The ongoing vigil of Tabby's star continues, not in search of aliens, but to understand the violent and dramatic lives of planetary systems and the hauntingly beautiful shadows their dust can cast. Just as astronomers were beginning to feel they understood the nature of these explosive events, the universe delivered a signal from a place it simply shouldn't have been. In early 2020, the CHIME telescope detected a new repeating fast radio burst, designated FRB 2020-0120E. It was a remarkable find in itself, but its true significance only became clear once the very long baseline array managed to pinpoint its origin with incredible precision. The location was not some distant star-forming dwarf galaxy or a bustling spiral. It was coming from within our own cosmic backyard, a mere 12 million light-years away in the majestic Whirlpool galaxy M101. And not just anywhere in that galaxy, but from one of its ancient, dormant globular clusters, a retirement home for stars, a place where the stellar fireworks that create magnetars were supposed to have ended billions of years ago. This placement was nothing short of revolutionary. Globular clusters are among the oldest structures in the universe, dense balls of hundreds of thousands of stars that formed over 12 billion years ago. Their stellar populations are ancient, the massive, short-lived stars that die in supernova explosions to create young neutron stars and magnetars burned out eons ago. Everything left is old, quiet, and slowly cooling. The dominant theory for repeating FRBs pointed squarely to young, highly magnetized neutron stars or magnetars born in the recent violent deaths of massive stars. To find an FRB engine in a globular cluster was like finding a roaring bonfire in the middle of a library's rare books section. It completely violated the established rules of where such energetic phenomena were supposed to occur. The immediate implication was profound. There had to be another way to make an FRB. The presence of this energetic object in such an ancient environment forced astrophysicists to consider entirely new formation channels. One compelling theory points to the incredibly dense environment of the cluster itself. In the crowded core of a globular cluster, stars don't lead solitary lives, they interact, sometimes violently. The most likely culprit for FRB 2020-0120E could be a recycled pulsar, an old neutron star that has been given a new lease on life. How through accretion? If this neutron star has a binary companion, perhaps a white dwarf or a low-mass star, it could be siphoning material from its partner. This steady inflow of matter could spin the neutron star up to incredible speeds and potentially re-energize its magnetic field, effectively turning a sedate old pulsar into a rejuvenated engine capable of producing these powerful bursts. This model elegantly explains how you can get a young phenomenon from an old star, all thanks to the unique social dynamics of a stellar city. Another, even more exotic possibility involves stellar collisions. In the dense dance of a globular cluster's core, direct collisions between stars, while rare, do happen over billions of years. A collision between two white dwarfs or between a white dwarf and a neutron star could potentially create a new, massive neutron star in a single instantaneous event. This newly formed object could be born with the rapid spin and intense magnetic field needed to power FRBs, even in an environment that hasn't seen a traditional supernova in billions of years. This scenario paints a picture of a sudden, violent rebirth in the heart of the ancient cluster, a one-off event that creates a powerful and persistent source. The discovery of FRB 2020-0120E did more than just add another strange object to the catalogue. It fundamentally expanded the playing field for where we expect to find these cosmic engines. It proved that the conditions for producing FRBs are not limited to the messy nurseries of young stars. They can also emerge in the quiet, ancient corners of galaxies through processes of stellar interaction and rejuvenation. This one signal, buzzing from a globular cluster, forced a major revision of our theories, demonstrating that the universe has multiple, diverse pathways to create these enigmatic bursts. It was a humbling and exhilarating reminder that cosmic rules are made to be broken, and that the most profound discoveries often come from the places we least expect to find them. While we often search for signals in the form of radio waves or strange stellar behavior, some of the universe's most profound messages are written across the entire sky, etched into the oldest light we can see. This brings us to a signal that isn't a burst or a beam, but a profound absence, a mysterious chill in the cosmic background radiation known as the cold spot. To understand its significance, we have to journey back almost 14 billion years to the very beginning of everything. After the Big Bang, the universe was a searing, opaque plasma of particles and energy. It wasn't until about 380,000 years later that it had expanded and cooled enough for atoms to form, allowing light to travel freely for the first time. That first flash of light, now stretched and cooled by the expansion of the universe, still fills all of space. We detect it today as a faint microwave static, a uniform glow coming from every direction. This is the cosmic microwave background, or CMB, and it is the universe's baby picture, a snapshot of its infancy. This background radiation is remarkably even, but not perfectly so. Tiny, tiny fluctuations in temperature, mere millionths of a degree, are imprinted upon it. These ripples represent the seeds of all future structure, the slight over-densities that would, over eons, gravitationally collapse to form galaxies and clusters. Mapping these fluctuations has been a primary goal of satellites like WMAP and Planck, and in these incredibly detailed maps, astronomers found something truly bizarre, a region in the constellation Eridanus that is significantly colder than the surrounding sky. This isn't just a minor variation, it is a large circular anomaly, a cold spot so statistically significant that it stands out as one of the most unusual features in the entire CMB. It is a cosmic bruise, a patch of cold that defies easy explanation. The most straightforward theory proposed to explain this chill is the existence of a supervoid. The idea is rooted in a subtle effect of cosmology known as the integrated Sachs-Wolf effect. As light travels through the universe, it climbs in and out of the gravitational wells of massive structures like galaxy clusters. If the universe was static, the energy lost climbing out would equal the energy gained falling in, and the net effect would be zero. But because our universe is expanding at an accelerating rate driven by dark energy, these gravitational wells are actually becoming shallower over time. This means a photon gains a little more energy falling into a well than it loses climbing out, resulting in a net blue shift or heating. Conversely, when light travels through a vast, under-dense region, the opposite happens. It experiences a net red shift, losing energy and thus cooling the CMB light that passes through it. So, if a truly enormous void sat between us and the cold spot, it could theoretically explain the temperature drop. The hunt for this proposed supervoid began, And indeed, astronomers did find a large void in that general direction, now known as the Eridanus supervoid. But there was a major problem: scale. The void is immense, nearly 1.8 billion light-years across, but it is not nearly immense enough, nor is it empty enough to account for the profound cooling observed in the cold spot. The numbers simply don't add up. The physics of the integrated Sachs-Wolf effect, as we understand it, cannot produce such a large temperature drop from a void of that size. It would require a void of such staggering proportions that it would challenge our understanding of the large-scale structure of the universe itself. The discovered void is impressive, but it is not the cosmic ghost town we need to solve this puzzle. With a simple void explanation falling short, cosmologists were forced to consider far more exotic and thrilling possibilities. One of the most compelling is the concept of a cosmic texture. This is not a physical fabric, but a topological defect in the very structure of spacetime itself, a kind of cosmic knot that could have formed during a phase transition in the early universe, a fraction of a second after the Big Bang. Think of it like the cracks and fissures that form in ice as water freezes. As the universe cooled and its fundamental forces separated, similar imperfections could have been frozen into the fabric of reality. If such a texture existed within our past light cone, its immense gravitational field would have left a distinct imprint on the CMB, a circular cold spot, exactly like the one we observe. This idea is profoundly beautiful because it treats the cold spot not as an anomaly to be explained away, but as a potential signal from the highest energy physics imaginable, a fossil from the first fleeting moments of creation. The implications of this are staggering. Confirming a cosmic texture would be direct evidence for grand unified theories, which attempt to describe how the fundamental forces of nature were once merged into a single superforce. It would provide a rare observational window into physics at energy scales 1 trillion times higher than what we can achieve in our largest particle colliders. The cold spot, therefore, becomes more than just a curiosity. It transforms into a potential messenger from the inflationary epoch, carrying information about the universe when it was less than a second old. It represents the tantalizing possibility that the largest structures we can observe in the sky are directly linked to the smallest, most fundamental laws of physics. The debate between the supervoid and cosmic texture explanations continues, a fascinating tug-of-war between a known but insufficient phenomenon and a speculative but elegant solution. Future galaxy surveys will map the large-scale structure in ever greater detail, seeking to definitively confirm or rule out the existence of a void large enough to be the culprit. Meanwhile, theorists continue to refine their models of exotic early universe phenomena, searching for other unique signatures a cosmic texture might leave behind. The cold spot endures as a perfect example of a cosmological mystery. It is a signal that requires us to question our understanding of gravity, of the universe's expansion, and of its very origins. It is a chill on the sky that invites us to dream of the universe's first moments, reminding us that some of the most important messages from the cosmos are not written in light, but in the subtle, cold silence between the stars. But if the cold spot presents a chilling stillness on the cosmic map, another discovery probes a different, more dynamic mystery, a ghostly current pulling entire clusters of galaxies in a direction that simply shouldn't exist. This is the enigmatic signal known as the dark flow. The story begins not with a flash of light, but with a meticulous study of the universe's oldest light, the cosmic microwave background. This afterglow of the Big Bang is the foundation of our cosmic rest frame. Its subtle temperature variations allow us to measure our own motion through the cosmos. We know, for instance, that our solar system is moving at a certain speed relative to this background, an effect we see as a Doppler shift, a slight warming in the direction we're heading and a cooling behind us. This is our local dipole. In the 2000s, a team of astronomers led by Alexander Kashlinsky decided to investigate whether this motion was purely local or part of something much larger. Using data from the WMAP satellite, they performed a remarkable feat of cosmic cartography. They identified hundreds of massive, distant galaxy clusters. Then, they meticulously subtracted all the known sources of motion, the expansion of the universe, the local gravitational pull of the Great Attractor, and our own solar system's movement. The question was simple. Once all that was stripped away, would these far-flung clusters show any residual common motion? According to the standard model of cosmology, the answer should have been a resounding no. On the largest scales, the universe is supposed to be homogeneous and isotropic, meaning matter is distributed evenly, and there should be no preferred direction for large-scale flows. The results were anything but quiet. Kashlinsky's team found a startling, coherent signal. Galaxy clusters spread across billions of light-years, from the relatively nearby to the extremely distant. All appeared to be streaming in the same direction at astonishing speeds of nearly 1,000 kilometers per second. This wasn't a gentle drift, it was a torrential flow, a concerted movement of thousands of galaxies towards a single point in the sky near the constellations Centaurus and Vela. This dark flow suggested that something immense, something beyond the horizon of our observable universe, was exerting a gravitational tug on everything we can see. The implications of such a discovery are revolutionary, and they immediately divided the cosmological community. The most extraordinary explanation points to the multiverse. If our universe is just one bubble in a vast, inflating multiverse, other bubble universes could exist beyond our cosmic horizon. A neighboring universe unimaginably close in the higher dimensional foam of space-time, yet completely separate from our own, could possess a vastly different distribution of mass. If it were massive enough and near enough, its gravitational influence could, in theory, reach across the void and pull on the matter in our observable universe, creating the coordinated stream we detect as the dark flow. This idea transforms the flow from an anomaly into a potential window, our first ever empirical glimpse into a reality beyond our own cosmos. Skeptics, however, argue for more mundane causes, primarily systematic errors in the incredibly complex measurements. The technique involves comparing the hot and cold spots in the CMB behind a galaxy cluster with the spots around it. Any misestimation of the cluster's own properties, such as the density and temperature of the hot gas within it, could introduce a false signal. Other critics suggest that the method of stacking data from so many clusters might be amplifying subtle, local effects into a false pattern that looks like a coherent flow. The Planck satellite, WMAP more advanced successor, later conducted its own analysis and found no evidence for the dark flow, dealing a significant blow to the claim and fueling the argument that the original detection was a persistent artifact. Yet the controversy has not been entirely put to rest. Proponents of the flow have countered that the Planck team used a different methodology and a different set of clusters, and that when applied consistently, a signal remains. They argue that the flow has been detected in multiple, independent catalogs of clusters, and that its amplitude appears to be consistent out to ever greater distances, which would be impossible if it were caused by a local structure. This back and forth highlights the immense difficulty of doing precision cosmology at the very edge of the observable universe, where the signals are faint and the potential for error is high. The dark flow remains one of cosmology's most contentious open cases, a tantalizing signal that sits precariously between a monumental error and a paradigm-shattering discovery. It challenges the very principle that our universe is a lonely, island cosmos, daring us to consider that the greatest forces shaping our reality may lie in the profound darkness beyond the light of our Big Bang. Rising from the heart of our galaxy like two colossal, silent ghosts, the Fermi bubbles are a testament to a violent, forgotten chapter in the Milky Way's history. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, These vast structures are not something you can see with the naked eye. They are revealed only in the high-energy light of gamma rays. They form a symmetrical hourglass shape, extending an astonishing 25,000 light-years above and below the galactic center. To grasp their scale, imagine that the entire visible disk of our spiral galaxy could fit between them. They are a pair of immense cosmic lungs, and roughly 10 million years ago, our galaxy took a tremendous energetic breath. The mystery lies in what powered this titanic exhalation. Gamma rays are the most energetic form of light in the universe, produced only by the most extreme processes. The fact that these bubbles are still emitting them today means they are filled with high-energy particles, primarily electrons, moving at nearly the speed of light. But what accelerator could have possibly launched these particles across such a vast volume of space? Astronomers are currently debating two main theories, each pointing to a different kind of cataclysm at the galactic core. The first and perhaps most dramatic theory involves our galaxy's own supermassive black hole, Sagittarius, a star. While it is quiet today, this gravitational monster, weighing 4 million times the mass of our Sun, may have had an active and violent past. The theory proposes that long ago, a vast cloud of gas or even a star ventured too close and was torn apart by the black hole's immense gravity. As this material spiraled into the accretion disk, it heated to incredible temperatures before finally plunging past the event horizon. But not all of it was consumed. In this model, a fraction of the inflowing matter was channeled and ejected along the black hole's spin axis at near light speed, forming two powerful jets that punched their way out of the galactic disk. These jets would have inflated the bubbles, filling them with fast-moving particles that continue to produce gamma rays as they interact with the ambient light and magnetic fields of intergalactic space. This would mean the Fermi bubbles are the fading scar of a past active galactic nucleus event, a relic from a time when our own galaxy was a quasar. The second major theory looks not to the black hole, but to the bustling stellar metropolis that surrounds it. The galactic center is the most crowded place in the Milky Way, home to intense regions of star formation. Within these stellar nurseries, stars are not just born, they also die, and they do so in spectacular fashion. The alternative explanation suggests that a sudden, intense wave of star formation occurred millions of years ago, creating a large population of massive, short-lived stars. These stars would have lived fast and died young, exploding as supernova in a relatively short period. The combined force of hundreds or even thousands of these consecutive stellar explosions could have created a powerful galactic wind, a shockwave of energy and particles that blew outward from the disk, inflating the bubbles in a more spherical, less focused manner than a black hole jet would. This scenario paints a picture of a starburst-driven phenomenon, where the collective death of stars reshaped the very halo of our galaxy. The truth may lie in a combination of these events, or perhaps something even more complex. Data from other telescopes, like the Planck satellite, which observed the bubbles in microwave light, have revealed that they also have a distinct and well-defined edge in what is known as the hard X-ray spectrum, suggesting they are a single, coherent structure with a defined shell. This supports the idea of a rapid, impulsive event rather than a slow, continuous process. Furthermore, the bubbles are connected to other mysterious structures near the galactic center, like the so-called microwave haze and a pair of even larger radio wave bubbles detected by the Mercator telescope, suggesting we are looking at a multi-layered, multi-wavelength phenomenon that is all part of the same immense outburst. What makes the Fermi bubbles so profoundly important is that they are not just a distant curiosity, they are a part of our galactic home. They reveal that the Milky Way is not a static, serene spiral. It has a dynamic and occasionally violent personality. Their existence forces us to reconsider the life cycle of a galaxy, showing that even seemingly quiescent ones like our own can experience these enormous energetic eruptions. They are a permanent record, a fossil imprinted on the sky, telling the story of a brief but incredibly powerful event that forever changed the environment above and below our galactic plane. Studying their structure, their energy, and their composition is like reading a history book written in gamma rays, detailing a time when the center of our galaxy roared with an energy that echoed for tens of thousands of light years. While we often search for signals in the realm of radio waves and flashing light, some of the universe's most profound messages are written in the subtle thermal glow of dust. Scattered throughout the vast clouds between the stars, a cryptic signature appears again and again in the data from infrared telescopes, a set of 4 specific emission features that have puzzled astronomers for decades. These are the unidentified infrared bands, or UIBs, and they represent one of the most widespread and important chemical mysteries in the galaxy. Unlike a single, fleeting burst, this signal is a constant, humming chorus, a testament to a complex organic chemistry operating on a truly cosmic scale. The story of their discovery begins with the dawn of space-based infrared astronomy. In the 1970s and 80s, as instruments were first lifted above Earth's obscuring atmosphere, they opened a new window onto the cosmos. When researchers pointed these telescopes at various celestial objects, planetary nebulae, regions of star formation, and even other galaxies, they kept finding the same peculiar pattern. The spectra, which are like chemical fingerprints showing how much light is emitted at each wavelength, revealed a series of strong, sharp emission peaks at specific frequencies: 3.3, 6.2, 7.7, and 11.3 micrometers. These weren't the broad, smooth features of hot dust or simple gases. They were narrow and distinct, the unmistakable signature of something more complex. The fact that they appeared in such a wide variety of environments, from the wreckage of dead stars to the nurseries of new ones, meant they were produced by a substance that was both incredibly common and remarkably robust. The hunt was on to identify the carrier of these bands. The leading, and now widely accepted, theory points to a fascinating and surprisingly familiar class of molecules: polycyclic aromatic hydrocarbons, or PAH. Imagine the basic structure of a pencil lead, graphite, which is made of flat sheets of carbon atoms arranged in hexagons. Now, imagine taking a small flake of that graphite, just a few dozen atoms across, and attaching hydrogen atoms to its edges. What you have is a pH molecule, a sturdy, plate-like structure that can vibrate in specific ways when energized by starlight. It's these molecular vibrations that are thought to produce the precise infrared emission features we detect. The 3.3 micrometer band, for instance, comes from the stretching of carbon-hydrogen bonds, while the 11.3 micrometer band is linked to carbon-hydrogen bending motions at the edge of the molecule. In essence, we are detecting the collective hum of countless microscopic carbon rings shaking and shimmying as they bask in the light of stars. The implications of this are staggering. pHs are not just some exotic curiosity. They are a fundamental and abundant component of the interstellar medium, making up a significant percentage of all the carbon in the galaxy. They are thought to form in the outflows of carbon-rich red giant stars, where conditions are just right for building these complex carbon structures atom by atom. Once forged, they are incredibly durable, able to survive the harsh radiation of interstellar space and even the violent shock waves of supernova explosions. Their prevalence tells us that the basic building blocks of soot are everywhere, and their study has given rise to an entirely new field of astrochemistry focused on these large organic molecules. They act as miniature interstellar engines, absorbing the high-energy ultraviolet light from young, massive stars and re-radiating it as this characteristic infrared glow, playing a crucial role in the thermal balance and energy cycle of galaxies. Perhaps the most profound aspect of the UIB signal is what it suggests about our own cosmic origins. PAHs are considered prebiotic molecules, complex organic compounds that are the potential precursors to the chemistry of life. The fact that they are so ubiquitous means that the raw materials for life are not confined to planets. They are sown throughout the galaxy, a natural byproduct of stellar evolution and chemistry. Everywhere new stars and planets form, these organic particles are there, perhaps raining down on young worlds and providing a head start for the chemical reactions that could eventually lead to living systems. The unidentified infrared bands, therefore, are far more than just a solution to an astronomical puzzle. They are a faint, warm whisper from the spaces between the stars, telling us that the universe is not only rich with the elements for life, but is already busy assembling them into complex forms long before they ever reach a planet. And just as we map the echoes of our galaxy's violent past, we are also pulled by a force from beyond, a silent, immense tug that guides the motion of our entire galactic neighborhood. This brings us to one of the most profound gravitational signals ever detected, a cosmic undertow known as the Great Attractor. For decades, astronomers have known that our Milky Way is not simply drifting aimlessly through the void. It is moving with a purpose, and everything around us is moving with it. Our local group of galaxies, which includes Andromeda and dozens of smaller companions, is streaming through space at a staggering 600 kilometers per second. This motion isn't random, it's a coordinated flow, a peculiar velocity that points with unnerving consistency toward a specific region of the sky deep in the constellation Centaurus. Something over there, something of unimaginable mass, is pulling us in. The search for the source of this pull led to the identification of a gravitational heartland, a concentration of mass so vast it dominates an entire region of space. This is the Great Attractor, a gravitational anomaly located approximately 250 million light-years away. It represents the core of our local supercluster, which astronomers call Laniakea, Hawaiian for immense heaven. The Great Attractor is the central hub around which our Milky Way, the Virgo cluster, and tens of thousands of other galaxies orbit, all drawn by its immense gravity. The problem, however, is that we can't actually see it. From our vantage point on Earth, the plane of our own galaxy blocks the view. This region, known as the zone of avoidance, is shrouded by thick clouds of gas and dust, along with the dense glitter of countless stars, making optical observations nearly impossible. It was as if we had deduced the existence of a hidden mountain range by feeling the wind flowing down from its slopes, but were unable to look directly at the peaks themselves. This visual obstruction turned the Great Attractor into one of astronomy's great blind spots for much of the 20th century. We could measure its gravitational influence with exquisite precision, charting the paths of thousands of galaxies all flowing in its direction, but the source itself remained a shadowy enigma. The breakthrough came not from trying to see through the galactic dust, but from looking with different eyes. Pioneering work using radio telescopes, which can pierce the dusty veil, began to reveal what optical light could not. Surveys like the Parkes High Zone of Avoidance, or HIZOA, project used the 21-centimeter emission line of neutral hydrogen to map the hidden structures behind our galaxy's bulge. What they found was breathtaking, previously unseen galaxies, large spiral systems and clusters, all lying in the direction of the Great Attractor, contributing to its immense gravitational pull. But the story didn't end there. As our maps improved, we realized the Great Attractor itself might be just a waypoint on a much longer journey. The peculiar motion of our local group toward it is only part of a larger flow, the same dark flow we discussed earlier, pulling us toward something even more massive and distant. The Great Attractor, with a mass equivalent to tens of thousands of Milky Ways, now appears to be itself pulled toward an even greater attractor, a colossus known as the Shapley supercluster. Located over 650 million light-years away, Shapley is the most massive known concentration of matter in our local universe, a sprawling metropole of galaxies containing dozens of rich clusters. The gravitational signal we feel is likely a combination of these two giants, the relatively nearby pull of the Great Attractor and the more distant, but even more powerful tug of the Shapley supercluster. Modern efforts to understand this cosmic current involve a multi-wavelength assault on the zone of avoidance. Infrared space telescopes like the Spitzer Space Telescope and the Wide Field Infrared Survey Explorer, or WISE, have been instrumental. Infrared light travels through dust much more effectively than visible light, allowing these observatories to peer through the galactic murk and catalog countless galaxies that were previously invisible. Each newly mapped galaxy adds a piece to the puzzle, helping to build a three-dimensional mass map of the hidden hinterlands behind the Milky Way. These surveys have confirmed that the region is teeming with large-scale structure, with massive clusters and long filaments of galaxies all contributing to the gravitational signal we detect. The ongoing study of the Great Attractor is a brilliant example of how science works around a problem. We detected its signal not by what we could see, but by what we could feel, its gravitational influence on everything around us. It is a phantom we have learned to map by the motions of its subjects. This grand cosmic flow reminds us that our place in the universe is dynamic and interconnected. We are part of a vast, gravitationally bound structure, forever in motion, drawn through the cosmos by the hidden architecture of mass itself. It is a silent, relentless signal written not in light, but in the very trajectory of our galaxy. Deep within the heart of our own galaxy, hidden behind thick veils of cosmic dust, another signal pulses with a mysterious and persistent energy. This is not a fleeting burst or a singular event, but a steady, unexplained glow that has become one of the most compelling puzzles in modern astrophysics. It's known as the galactic center excess, and it was discovered not by looking at the center of the Milky Way, but by meticulously subtracting everything else we expected to see there. Using data from NASA's Fermi Gamma-ray Space Telescope, astronomers were building a map of the high-energy sky, a landscape dominated by the violent deaths of massive stars and the intense winds of pulsars. But when they carefully removed all these known sources of gamma radiation, a strange, residual glow remained, a smooth, symmetrical haze of excess gamma rays emanating from the region around the supermassive black hole Sagittarius, a star. This glow was too perfectly centered and too evenly distributed to be explained by any known population of celestial objects. It was as if the very core of our galaxy was whispering a secret in the language of the universe's most energetic light. The most tantalizing explanation for this excess points to the very nature of the invisible universe itself, dark matter. We know dark matter exists because of its gravitational pull on galaxies, but we have never directly detected a single particle of it. Theorists propose that one candidate for this mysterious substance is a class of particles known as weakly interacting massive particles, or WIMP. If these particles exist, they could be their own antimatter counterparts. This means that when two WIMP collide, they would annihilate each other in a flash of energy, producing a cascade of secondary particles that would ultimately decay into gamma rays. The density of dark matter is believed to be highest at the center of galaxies, precisely where this gamma-ray excess is detected. The signal's smoothness and symmetry are exactly what many models predicted for a dark matter annihilation signature, a faint but omnipresent fireworks display from the ghostly halo of matter that holds our galaxy together. For many, the galactic center excess represents our best and most promising chance to finally move dark matter from a theoretical concept into the realm of observable physics. Yet, the universe is a master of ambiguity, and an alternative explanation emerged from a more conventional celestial census. The central bulge of the Milky Way is one of the most crowded stellar neighborhoods imaginable, a dense metropolis of stars of all ages. Among this ancient population, there could be a vast, unseen army of millisecond pulsars. These are neutron stars that have been spun up to incredible speeds by siphoning material from a companion star, and they emit powerful beams of gamma radiation. Individually, they would be too faint and too numerous for Fermi to resolve against the bright background of the galactic center. but collectively, their combined emission could perfectly mimic the smooth, haze-like glow that we attribute to the excess. It's the difference between seeing a single distant light and seeing the combined glow of a sprawling city from miles away. The individual sources blur into a uniform sheet of light. The debate between these two ideas, dark matter annihilation versus a pulsar population, has driven a decade of intense scientific investigation. To distinguish between them, researchers have looked for the telltale sign of a point source. If the glow is made of thousands of faint pulsars, then with sufficiently sensitive observations, the smooth haze should break down into a granular field of individual points of light. Some analyses of the Fermi data have claimed to find evidence for such a granular structure, bolstering the pulsar argument. However, these findings are hotly contested, with other teams arguing that the statistical methods used can create the illusion of points where none exist. The hunt for a smoking gun continues, with radio telescopes scanning the same region, searching for the faint, telltale radio pulses that would confirm the presence of these spinning stellar corpses. The true power of this signal lies in its ability to force us to improve our tools and challenge our assumptions. It is a mystery that sits at the intersection of particle physics and astronomy, requiring experts from both fields to work together. Whether the final answer points to a revolutionary new particle or a previously unrecognized stellar population, the galactic center excess has already proven its value. It has sharpened our questions, refined our models, and demonstrated that sometimes the most important discoveries are not the dramatic bursts, but the patient, persistent glows that force us to look deeper, think harder, and truly see what has been hidden in plain sight all along. For centuries, sharp-eyed lunar observers have documented something strange happening on the surface of our nearest celestial neighbor. These are not the steady, familiar features of the moon, but fleeting, unpredictable events. Sudden flashes of light, patches of color, or areas that appear to momentarily cloud over or brighten. These mysterious occurrences are collectively known as lunar transient phenomena, or LTP, and they represent a signal of an entirely different kind, one that suggests the moon is not the completely dead and static world we often assume it to be. The history of these observations is rich and stretches back to before the invention of the telescope. One of the earliest recorded instances dates back to the year 1178, when a group of English monks reported seeing flames and glowing embers on the moon during an eclipse, a sight so alarming they believed it was a sign of impending doom. In the 18th and 19th centuries, renowned astronomers like Sir William Herschel, the discoverer of Uranus, reported seeing red glows on the lunar surface, which he speculated could be evidence of active volcanoes. The advent of powerful telescopes only added more reports to the catalogue. Throughout the 1950s and 60s, as the space race heated up, both professional and amateur astronomers meticulously documented these events. They described vivid flashes that could last for seconds or minutes, localized areas of obscuration that made craters appear to vanish behind a temporary haze, and even subtle color changes, with some observers reporting reddish or purplish tints. These weren't just random claims, they often came from highly experienced observers at major observatories. The sheer volume and consistency of these reports, spanning different cultures and centuries, strongly suggested that something tangible was occurring on the lunar surface. It wasn't mere optical illusion or atmospheric distortion. The moon itself seemed to be speaking in a language of brief, enigmatic flickers. In the modern era, the quest to verify and understand these phenomena has moved from the notebooks of lone astronomers to organized scientific campaigns. Projects like the Association of Lunar and Planetary Observers have dedicated sections for volunteers to systematically monitor and report LTP. But the most compelling evidence has come from more advanced technology. Since 2005, a team led by the European Space Agency has been operating a dedicated lunar monitoring telescope, automatically scanning the moon's dark side with two high-sensitivity video cameras. This project has been remarkably successful, detecting hundreds of these fleeting flashes, proving definitively that the events are real and not a trick of the eye. This systematic data collection has been crucial, transforming LTP from anecdotal curiosities into a legitimate field of planetary science. So what could be causing these strange lunar signals? Scientists have proposed several compelling natural explanations, each fascinating in its own right. The leading theory points to a process called outgassing. The Moon's interior, while largely cool, is not entirely inert. It contains traces of radioactive elements that decay and produce heat, and it may still hold pockets of trapped gases like radon or argon from its formation. As the Moon's crust is stressed by the gravitational pull of the Earth, a force that creates the tides in the solid rock of the Moon itself, tiny fissures could open, allowing these trapped gases to vent into the vacuum of space. When this gas is exposed to sunlight, it could become ionized and glow, or it could kick up incredibly fine dust from the surface, creating a temporary, shimmering cloud that obscures the terrain below. This would explain the hazy patches and dimming reported by observers. Another major cause is almost certainly meteoroid impacts. The Moon has no atmosphere to protect it, so even tiny pebbles from space strike its surface at tremendous speeds. When a meteoroid, perhaps no larger than a walnut, slams into the lunar soil, the kinetic energy of the impact is instantaneously converted into heat and light, creating a brilliant flash visible from Earth. The European monitoring system has captured countless of these impact flashes, particularly during known meteor showers like the Geminids or Perseids, when the Moon plows through a denser stream of cosmic debris. These events are a stark reminder that the solar system is a dynamic shooting gallery, and the Moon's scarred face is constantly being subtly reshaped. Other theories, while less common, are equally intriguing. Some scientists have suggested that electrostatic phenomena could be at play. The lunar surface becomes highly electrically charged by the solar wind. It's possible that this built-up static electricity could suddenly discharge, leaping from grain to grain of lunar soil like a miniature lightning bolt, creating a tiny, localized flash. There's also the possibility that some rocks on steep slopes could be dislodged by thermal stresses. The extreme temperature shift between lunar day and night, creating tiny avalanches that expose fresh, brighter material underneath, appearing as a small, moving glint of light to a powerful telescope. The true significance of lunar transient phenomena lies in what they tell us about the Moon's present state. If outgassing is indeed a real and ongoing process, it means the Moon has a faint, residual geological heartbeat. It's not a frozen fossil, it's a world with a subtle, ongoing internal activity. For future lunar exploration, this is critical information. These outgassing sites could be valuable sources of resources, potentially providing water, ice, or other volatile compounds trapped in the soil. They also represent a potential hazard, as the release of gases could undermine the stability of a future lunar base. By treating these fleeting lights not as myths but as genuine signals, we are learning to listen to the Moon's quiet whispers, gaining insights that will guide humanity's next steps as we return to and eventually inhabit our celestial companion. While we search the cosmos for signals from distant stars, sometimes the most perplexing messages come from our own robotic ambassadors, revealing that we still have much to learn about the laws of physics right here in our own solar system. This brings us to the Pioneer anomaly, a decades-long mystery that began not with a flash or a burst, but with a persistent, subtle drift in the paths of two of humanity's most intrepid explorers. The Pioneer 10 and Pioneer 11 spacecraft were launched in the early 1970s on grand tours to the outer planets before they continued on into the eternal darkness of interstellar space. As they journeyed farther from the Sun than any human-made objects had before, NASA engineers meticulously tracked their positions using the Doppler effect, measuring the precise frequency of their radio signals to determine their speed and trajectory with incredible accuracy. And that's when they noticed something was wrong. According to the well-established laws of orbital mechanics, the primary force acting on the probes as they raced toward the edge of the solar system should have been the sun's gravity, pulling them back and causing a very predictable, very slight deceleration. But the data told a different story. Both spacecraft were slowing down just a tiny bit more than expected. This extra deceleration was minuscule, about 10 billion times weaker than the gravity we feel pulling us to the Earth's surface, but it was constant, unidirectional, and most bafflingly identical for both probes. It was as if a faint, unseen hand was reaching out from the direction of the sun, applying a gentle but persistent brake on their journey to the stars. For over 20 years, this anomaly persisted in the data, a quiet, unsolved puzzle that gnawed at physicists and engineers. The consistency of the signal made it impossible to ignore. Year after year, as the pioneers sailed onward, their radio signals continued to show that same unexplained drift. The tiny anomaly became a monumental problem because it challenged the very foundation of our understanding of gravity, Einstein's general theory of relativity, which had predicted every other gravitational interaction with perfect precision for nearly a century. The most thrilling and radical explanation proposed was that our theory of gravity itself was incomplete. Perhaps on the very large scale of the solar system, or in the extremely weak gravity regime the probes were experiencing, Einstein's equations needed a small modification. Theories like modified Newtonian dynamics, or MUND, which were initially developed to explain the rotation of galaxies without dark matter, were suddenly looked at as potential solutions for the pioneer puzzle. For a time, it seemed like these two humble probes might have stumbled upon the first cracks in our most successful theory of the universe, a discovery that would have been one of the most profound in the history of science. Yet, the most extraordinary claims require the most extraordinary evidence, and in science, the most likely explanation is often the most mundane one hiding in plain sight. A large team of researchers embarked on a painstaking forensic investigation, not with new telescopes, but with old engineering documents, computer models, and a deep understanding of the probes themselves. The pioneers were nuclear-powered, generating electricity from the heat of radioactive plutonium. That heat had to go somewhere, and it was dissipated into space through their large antenna dishes. The breakthrough came when the team realized that this heat radiation didn't just vanish, it carried momentum. Every photon of heat radiating from the spacecraft acted like a tiny photon rocket, imparting a minuscule push in the opposite direction. The team built an incredibly detailed thermal model of the entire spacecraft, accounting for the heat flowing from the power source, bouncing off internal components, and finally radiating into space from the antenna dish. When they calculated the net effect of all these tiny pushes, they found it created a constant sunward pressure that perfectly matched the anomalous deceleration. The mysterious signal wasn't a new force of nature. It was the ghost of the spacecraft's own warmth, a gentle thermal breeze that had been slowing them down all along. The resolution of the Pioneer anomaly stands as a brilliant testament to scientific diligence and a powerful cautionary tale for anyone interpreting cosmic signals. It reminds us that before we invoke revolutionary new physics to explain an observation, we must first exhaust every possible prosaic explanation, no matter how complex or tedious the investigation may be. It underscores the critical importance of understanding your instrument, whether that instrument is a giant telescope or a simple spacecraft. Unexpected behavior can often be traced back to the machine itself. The story also highlights the value of archival data and long-term monitoring. The anomaly was only solvable because decades of precise tracking data existed, and because a dedicated team was willing to dive into decades-old engineering blueprints to find the answer. The pioneers' long goodbye taught us a humbling and crucial lesson. Sometimes the universe isn't speaking to us in the mystery. Sometimes we're just listening to the echo of our own creations. From the fleeting, electrifying shout of the wow signal to the profound gravitational undertow of the Great Attractor, these 25 enigmatic messages from the cosmos paint a stunning portrait of a universe that is anything but silent. We've journeyed through the bizarre and the beautiful, from the millisecond fury of fast radio bursts to the patient, century-long dimming of a distant star. We've encountered signals that are whispers, like the faint and controversial SETI 02 plus 14a, and others that are earth-shattering proclamations, like the gamma-ray glow from the heart of our own galaxy that might just be dark matter finally announcing its presence. We've seen how a misunderstood microwave oven could mimic a cosmic event, and how the gentle heat of a spacecraft could masquerade as a new law of physics. This incredible diversity itself is the most powerful signal of all. It tells us that the universe communicates in a spectrum of languages, from the energetic flash of light to the silent, relentless pull of gravity, and it requires us to be multilingual in our curiosity. What these mysteries teach us above all is a profound lesson in humility. Each time we believe we have the cosmos figured out, it delivers a new puzzle that challenges our foundational assumptions. The repeating rhythm of FRB 180916 suggests an order we don't yet comprehend, while the impossible placement of an FRB in an ancient globular cluster reveals formation pathways we never imagined. The cold spot on the CMB dares us to consider flaws in our standard model of cosmology, or even glimpses into a multiverse. These aren't failures of our science, they are its fuel. They are the unanswered questions that propel generations of astronomers, physicists, and engineers to build better telescopes, devise more clever experiments, and think more creatively about the nature of reality itself. They remind us that the universe is not a puzzle to be solved, but an endless frontier to be explored, a dynamic and evolving story in which we are both the audience and the authors of each new chapter. This shared sense of wonder is what connects us all. Whether you're a professional researcher analyzing data from $1 billion observatory or someone simply gazing up at the stars from your backyard, that feeling of awe is the same. It's the driving force behind every discovery, the spark that ignites our collective imagination. So keep looking up, stay curious, question everything. The next great cosmic mystery might be hiding in plain sight, waiting for a fresh pair of eyes or a new way of thinking to bring it into focus. The universe is still speaking, we just have to continue learning how to listen. Now, we want to hear from you. After this journey through some of the greatest enigmas of space and time, which one captures your imagination the most? Was it the tantalizing possibility of the wow signal, the structured rhythm of a repeating FRB, or the haunting mystery of our galactic visitor, Oumuamua? Share your favorite cosmic signal in the comments below and tell us why it resonates with you. Let's keep this conversation going, because the search for understanding is a quest we all share, and the next great discovery could begin with a simple question from anyone, anywhere, who dares to look up and wonder.